Swayam Prabha. Digital India. Educated India.
Welcome back, my dear friends. A very good morning, good afternoon and good evening to all of you. We are in the 38th lecture for the TQM2 course under the NPTEL MOOC series, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember, we in the last two lectures for the last week, which is the 36th and 37th lecture, we didn't cover much of the slides, but we had a lot of discussions about regression model, multiple linear regression model, how you find out the estimate of beta, how you find out the sum of the square of the errors, then how you find out the variance for the betas, then the covariance of the betas, then sigma square, what is the degrees of freedom, and obviously I kept repeating what are the assumptions and how you do the QQ plots, how you do the plots of the errors with respect to x1, x2, x3, whichever variable which are there. The assumptions being that normality holds true for all the x's, for the errors, for the y's, then the expected value of the errors is 0, variance is all obviously there, and all these things. Then we slowly went into the 2 to the power k fractional factor models, considering there are k variables, they are two different levels 0, 1, minus 1, plus 1, and so on and so forth, and we saw that how the concept of orthogonality can be brought into the picture and we can model in the multiple linear regression models. And we were discussing that y is the variable and there are beta naught, beta 1, beta 2, beta 3, which means there is x1, x2, x3 variables based on which we can proceed, and we can find out the errors and the variances of the beta naught, variances of beta 1, beta 2, beta 3, where the variances of beta 1, beta 2, beta 3 for the last example which we were discussing in the 37th lecture, all the variances were equal, because for the orthogonality one. And I did mention time and again the concept of degrees of freedom. You are losing the degrees of freedom as you add more and more variables which are the independent ones which basically affect the value of y. So, continuing the discussion. So, if you have the output for the viscosity regression models, the actual viscosity which is y is given by beta naught hat, which is 1566 plus beta 2 hat, beta that was beta naught hat. So, this will be beta 2 hat, which is 7.62 into temperature is x1, plus 8.52 which is beta 2 hat into the feed rate. And if you see the constants, so which is what is interesting, I want to note down, I will highlight. So, these were the coefficients value is 1.1566.08 which is here, 7.656213 which is here, 8.585 which is here. The standard deviations or the standard errors for the constant one, obviously because they are estimates would basically have expected value, and if there is an expected value they are random and there would be a variance for that. So, variance for all these three constant, which is beta naught, temperatures coefficient which is beta 1, and feed rate coefficient which is beta 2, their standard errors are given. So, note down for a value of 1566 the standard error deviation is about 61, for 7.62 it is 0.61, for 8.5 it is 2.4. The temperature difference values which you remember T plus and T minus, and the p values level of significance. The r square value is given as 92.7, adjusted r square is given as 91.6. What adjusted r square basically considers the degrees of freedom into its picture, that is all, in a very general layman terms I am saying. So, r square basically gives you the level of prediction we are able to do. So, if it is 92.7, that means we are able to predict about 92% of the variations of y with respect to x. Obviously, 100 minus 92 would be the effect of white noise or the errors. The adjusted R square, when we bring the degrees of freedom into the picture, so it comes out to be about 91.6. That means 100 minus 91.6 is the overall errors or the prediction which you are not able to predict using the x's, which is basically given by the white noise. The analysis of variance, again we go back to the general main theme of our discussions. You have a table, the reading, all the variables or the attributes are there on the first column, then second column you have the sum of the square errors, you have the third column you have the degrees of freedom, you have the f value, because you want to test the null hypothesis whether it is true or false, and you have the degrees of level of significance. So, these are the sources, these are the degrees of freedom, these are the sum of squares. In our general table, this sum of the squares comes here, degrees of freedom comes here. You have the mean square errors, which is division of the sum of the squares by the degrees of freedom, the f value and the level of significance. So, based on that you can calculate and do the ANOVA table for the regression model also. 2 to the power 3 factorial design with mixing observations. So, you are mixing the observations. Consider the 2 to the power 3 factorial design with 4 center points from the same example. Suppose that when this example was performed, the run with all the variables at high level run were missing. This can happen for a variety of reasons, that the measurement errors was there. Measurement system can produce a faulty reading, the combination of the factor levels are not feasible, infeasible, they were not tempered or tuned as per the experiment, and so on and so forth. Or the unit was damaged, we did not get that unit, or we missed the unit, or the person who was taking the reading was not attentive, and all these reasons can be there. Again the same model, y is equal to beta naught, but beta 1 into x1 plus beta 2 into x2 plus beta 3 into x3 plus epsilon, again is the multiple linear regression model. Beta naught, beta 1, beta 2, beta 3 are the regression coefficients with respect to beta naught is when is basically the point at where it is cutting the y axis. Beta 1, beta 2, beta 3 are the partial regression coefficients or the rate of change of y with respect to x1, x2, x3 respectively. Using the 11 remaining observations, the x matrix is of this form, which is basically n cross 4. 4 means beta naught, beta 1, beta 2, beta 3. So, if there are x1, x2, x3, so it will be n cross 4 because the fourth one is basically coming for beta naught. Y values is again n cross 1. The x transpose x values is found out here, which I am just circling. You can use simple Excel sheet or a Minitab or a MATLAB to find it. Then x transpose y is given, from that you can find out beta hat. So, beta when I am mentioning betas or the x's or the y's are all vectors, matrices, vectors, scalar would only come for the case when you are trying to find out the sigma square. So, in beta, because there is a missing observation, the design is no longer orthogonal. When we find it out, the beta hat values comes out to be 51.25. This is beta naught hat, beta 1 hat is 5.75, beta 2 hat is 10.75, beta 3 hat is 1.25. Therefore, the fitted model is obviously there would not be an error term. So, if you want to find out the nth plus 1 value, it will be y hat nth plus 1, which is in the suffix, would be 51.25, which is beta naught hat, plus 5.75, which is beta 1 hat into x1. This is the first value, the first x value, and its corresponding reading is the nth plus 1. Then in plus beta 2 hat, which is 10.75 into x2, and its corresponding value is the nth plus 1 for the second variable, plus beta 3 hat, which is 1.25 multiplied by x3 and its corresponding x3 value being the nth plus 1. So, from that we can find out y hat, then find out the difference between y and y hat for the nth plus 1, nth plus 2, nth plus 3. N is basically depending on at which stage you are, which reading you are. Find out the errors, plot the errors with respect to x1, x2, x3, find out the averages values come out to be 0, yes or no, then plot the values of errors errors which should be normally distributed with respect to the standard normal distribution. You use the QQ plots, plot it along the 45 degrees line, check whether they are there. Obviously, they would not be all lying on the 45 degrees line, but you can get an answer for that. Compare this model to the obtained earlier. The regression coefficients are very similar because the regression coefficients are closely related to the factor effects. So, what is the effect of the factors? That what is the effect of x1 on y? What is the effect of x2 on y? What is the effect of x3 on y? So, they would be given by beta 1, beta 2, beta 3, but we are using the small sample or sample whatever it is to predict their values using the estimate beta 1 hat, beta 2 hat, beta 3 hat. Obviously, we will use beta naught hat to find out beta naught. However, notice that the effects estimates are no longer orthogonal because x transpose x and its inverse are no longer orthogonal. Furthermore, variances of the regression coefficients are larger than when it was the original data, because you have basically shrunk your sample size to a smaller sample size. When running a design experiment, it is sometimes difficult to reach and hold the precise factor levels required by the design. Small discrepancies are not important. So, obviously, they would be, but large ones are potentially of more concern to us and we should be careful. Regression methods are useful in the analysis of the designed experiments where the experimenter has been unable to obtain the required factor levels at what factors they are. To illustrate the example, where many of the test combinations are not exactly the ones specified in design, most of the difficulty seems to have been occurred with the temperature variable. So, again I am noting down or presenting to you the experimental design for the example, where you have the run given in the first column, the temperature which is the x1 variable at the second, pressure which is x2 in the third, and concentration which is x3 on the fourth. The coded variables are basically done accordingly such that you can find out the average values and note it down, and the y yield which is the dependent variable which is given on the last column. We will fit the main effect model, again the same model, y is equal to beta naught plus beta 1 into x1 plus beta 2 into x2 plus beta 3 into x3 plus epsilon, and y hat would basically be is equal to beta naught hat plus beta 1 hat into x1 plus beta 2 hat into x2 plus beta 3 hat into x3 plus, obviously there is no error. The x matrix is given, the y matrix is given. From this we find out the x transpose x and x transpose y. From that we find out the beta hat vector. So, the vector comes out to be after all the calculations, because the formula all which I am circling always remain the same. You do not have to worry. Once actually the basic concept is sum of the squares, partially differentiate with respect to the betas, put it to 0. Those are the orthogonal equations. Find out the hats, and after that your job is done, you proceed with the calculations. The values of beta naught is given as beta naught hat is 50.49. I am only reading till the second place of decimal. Beta 1 hat is 5.40, beta 2 hat is 10.16, beta 3 hat is equal to 1.07. The fitted regression model now would be y hat is equal to 50.49 in plus 5.40 into x1 plus 10.16 into x2 plus 1.07 into x3. So, this is what is given. Comparing this with the original model where the factor levels were exactly those specified by the design, we note a very little difference. The practical interpretation of the results of the experiment would not be seriously affected by this. Hence, we are able to utilize this model convincingly. So, even if there is inability on the experimenter side, like missing data was there, or the machine was not working to measure it, or the temperature difference was there, still there is no problem because the errors are very small. Errors with respect to the betas and the error terms. And obviously, we would for all these things, I am skipping it for the last example. We will draw the QQ plots, draw the error term on the y axis with respect to x1, x2, x3, and do all the comparison to find out the mean of the errors is 0. The variability of the errors should be sigma square hat, which you want to find out, and the normality conditions would also hold true. We will find out the covariance of beta vector. So, where the principal diagonal will be the square of the standard error of the betas, and of the diagonal element with the covariances existing between the betas. We observed that it is possible to deanalyze the interaction in the fractional factorial design by a process called folded over. So, you fold it and try to basically consider in using block design also. For resolution of 3 degrees or 4 degrees, a full fold over is constructed by running a second factorial in which the signs are reversed from those in the original factors. Then the combined design can be used to de-alias all main effects from the two factor interactions and basically have a better picture at how the effects are being done. A difficulty was with a full fold over is that it requires a second group of runs of identical sizes, but there the data size may not be applicable because the number of observations which we have for the sample is low. It is usually possible to realize certain interaction of interest by augmenting the original design with fewer runs than required in a full fold over. The partial fold over technique was used to solve this problem because we would not do the folds in at one go for considering all of the observations at one go. We will partially break into samples and then do the folds. The regression methods are an easy way to see how the partial fold over technique works and in some cases find even more efficient fold over design methods. To illustrate, suppose that we have a model of 2 to the power 4 minus 1 and fourth design model, and it shows that in which we consider the I matrix or I value as the factors A, B, C, D. Suppose that after the data from the first 8 trials are observed, the largest effects were basically A, B, C, D. So, we ignore the 3 factor interactions and the A plus B, A B plus C D alias chains are ignored. The other 2 alias chains can also be ignored, but clearly either A, B or C, D or both the 2 factors are large, hence they cannot be ignored. To find out which interactions are important, we could of course run on the alternative fraction which would require another 8 trials. Then all these 16 trials could be used to estimate the main effect and the 2 factor interaction. An alternative would be to use a partial fold over involving 4 additional runs and we can complete the task accordingly. So, again now as we are considering the partial fold of a model, so obviously the multiple linear regression would be larger in size, and what is that? Please pay attention to here. It is possible to realize A, B and C, D in fewer than 4 additional trials, hence we will assume the model as such. Initially what we had y is equal to, because there was no fold, so it was y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Now the model is changing. What is it? Please pay attention. It will be y is equal to beta naught plus beta 1 beta 1 into x1 plus beta 2 into x2 plus beta 3 in x3. This remains as it is. Now we are basically considering those extra factors as it should be as per the fractional factorial models considering the partial folds. The fifth term would be x4 into beta 4 plus beta 1 2, where you are combining the effect of A and B, which is x1 into x2, and the last term would be, apart from the error term, would be beta 3 into beta 3 4, which will be x3 into x4 plus epsilon, where the factors x1 x2 x3 x4 are the coded variables representing A, B, C, D, and the combinations of x1 x2 or x3 x4 would be the combinations of A, B and C, D. Using the design, the X matrix would now be given by n remains the same, but the factors which is n cross k plus 1 or n cross k plus 2, whatever it is, would now depend on the factors which you have considered. What are the factors? It is x1, x2, x3, x4, x1 and x2, which is the fifth one, and x3, x4, which is the sixth one. So, obviously, it will be n cross 7, because the seventh one means, which is the first one, would be beta naught. So, there would be beta naught, beta 1, beta 2, beta 3, beta 4, beta 1, 2, beta 3, 4. Where we have written the variables above the columns to facilitate a better understanding. Notice that x1, x2 column is identical to x3, x4 column, because AB or LISCD are coded as x1, x2 and x3, x4 respectively, implying a linear dependence model. Therefore, we cannot estimate both x1, x2 and x3, x4 in the model. However, suppose that we add an additional run and basically consider the x1, x2 as different levels, we can basically have alternate fractions to the original 8 runs and basically be able to estimate beta naught, beta 1, beta 2, beta 3, beta 4, beta 1, 2 and beta 3, 4. Once we have that matrix, it is again of size n cross, I am repeating the word n in order to basically denote the number of observations, n cross 7, Notice that the columns x1, x2 and x3, x4 are now no longer identical, and you can fit the model including and try to find out the estimates of beta 1 2 hat and beta 3 4 hat. 3 4 basically these are the suffixes. The magnitude of the regression coefficients will give insight regarding which interactions are important. So, once we do that, we can basically do the same methodology, trying to basically find out the beta hats, try to find out the errors, try to fit in the model to find out the average of the errors, try to fit and find out the distribution of the errors, and everything and would basically remain the same. And obviously, we will come into the main table, which is for the ANOVA, where the reading on the variables of the attributes. I am using the attributes because it can be attributes and variables also depending on what type of model you are considering. Then you have the sum of the squares, you have the degrees of freedom, you have the f values, on the mean square values, you have f values, and basically you have the level of significance. We have assumed the block factors were at the level of minus in the first 8 runs, then at the high level during the 9th run. It is easy to see that the sum of the cross products of every column with the block columns does not sum to 0, meaning that blocks are no longer orthogonal to treatment, or that the block effect now affects the estimates of the modular regression coefficients. To block orthogonality, we must add an even number of runs. For example, we have extra 4 runs where it will give us, because there are x1 x2 and x3 x4 combined, which is a b and c d. So, hence we basically add up more number of combinations for that, such that we can basically do the calculations and try to basically differentiate the effects in much better fashion. So, with DLISS for a b, which is x1 x2 and c d, which is x3 x4, and allow orthogonal blocking, this is equivalent to a partial fold over in terms of the number of runs and that are required in order to estimate. Now, we want to do the hypothesis testing. Again, we are going to come back to the ANOVA table. So, the test of significance for regression is to test to determine whether the linear relationship exists between the response variables y and a subset of regression variables x1, x2 till xk. Now, the actual hypothesis would be stated, which is in H naught case we will consider beta 1 to beta k all to be 0, and in H1, which is the alternative one cases, we will consider that for at least one of these j's, j is equal to 1 to k, they are not 0. So, in this case 0 means the effects of them are 0. That means, when you do the partial differentiation, the rate of change of y with respect to beta 1 x1 x2 x3 whatever is 0. That means, they are not being affected. So, rejection of H naught in this equation implies that at least one of the regression variables x1 to x3 contributes significantly. So, that means, if you are rejecting H naught, we will basically be taking cognizance of the fact that HA is true. So, if HA is true, that means one of the betas are definitely not equal to 0, which means that there is a linear relationship between y and that particular x. The test procedure involves an analysis of the variance exactly as the ANOVA table. We find out the total sum of the squares into sum of the squares due to the model and due to the sum of the errors. So, total sum is equal to sum of the variables plus sum of the errors. So, this is the main thing which we have been discussing, and from there we will basically do the ANOVA table. Now, if the full null hypothesis, which is H naught, is true, then SSR, which is for the regression models, divided by sigma square is distributed at chi square, because chi square is basically the distribution we will consider with respect to sigma square and the standard error distribution which we are considering, where the number of degrees of freedom of chi square is equal to the number of regressors variables in the model. Also, we know that the sum of the squares of the error by sigma square is distributed again chi square with a certain change in the degrees of freedom, and that the sum of the square of the errors and some of the squares of the total effects are independent. That is what is very important to note down, considering the fact we are considering normal distribution to be true for all the x's, errors and y. This is very important to be noted by all of you who are basically listening to this lecture and who are taking this course. The test procedure would be basically for H naught would be to find out f statistics, which is sum of the squares of the case divided by k, which k is the degree of freedom depending on the number of variables, divided by sum of the square of the errors divided by its degree of freedom. That will give me the mean square of r by divided by mean square of the errors. and we will reject if H naught F naught under H naught exceeds that value of F alpha. Alpha is the level of significance which you have. Alternatively, we could use the p values to approach to test the hypothesis and reject F naught if the p value of the statistics F naught is less than alpha, or if it is greater than alpha, we accept that alpha can be 1%, can be 5%, can be 10%, so on and so forth. The test statistic is usually summarized again in the same ANOVA table. So, what we have is this. You have the regressors, errors and the residuals are given in the first column. The sum of the squares is given, degrees of freedom is given, divide SSR by K is given by the mean square errors, SSE by n minus K minus 1 will give me the mean square errors. Based on that, you can find out the F statistics, and then we can comment whether it's right or wrong depending on the alpha value, which is the level of significance. The regression sum of the squares by the formula is given by beta hat transpose. So, beta hat what basically of size k plus 1 cross 1. So, it transpose would be just the opposite, multiplied by x transpose into y minus the overall effect of y's, which y's are the actual value divided by this. So, this is the basically the best fit line which you have for the actual value, and the error sum of the squares would be given by the, this is the total error minus this would give me the sum of the square of the errors. So, the total value would be given by addition of them, and you can find out the calculated values accordingly. So, in the following slide, it will shows the sum of the output from the Minitab for the viscosity regression model. The upper portion of the display is the analysis and variance for the model. The test of the significance of the regression in this example involves the hypothesis the beta 1 is equal to beta 2 is equal to not 0, and in the alternative one would be at least one of them is not 0. The p value of the table for the F statistics is very small. So, we would conclude that at least one of the variables, which is temperature or feed rate, have a non-zero value, hence the linearity relationship holds. The table also gives us the r square value, which is the adjust r square and the adjusted r square. R square would be the sum of the squares which are we are able to predict from the variables divided by the sum of the total errors. So, that would also be equal to 1 minus, because the ratio is always 1 for the total versus total minus the sum of the squares by the errors by the total. Just and in design experiment, r square is the measured amount of deduction the variability of y obtained by using the regression variables x1, x2, x3 till xk. However, as we have noted previously, a large value of r square does not necessarily imply that regression model is a good one. This is interesting, and listen to it. Adding a variable in the model will always increase r square, obviously, because you are adding more and more variables. We think that we are able to predict more and more, regardless of whether the additional variable is statistically significant or not. Thus, it is possible for models that have large r values to yield poor prediction of the new observation or estimates of the mean values as we proceed for the nth plus prediction, nth plus 2 predictions, and so on and so forth. So, basically we should take the minimum number of x's, try to predict the maximum, and basically have a value of r square where it will be able to give us the predicted errors as least as possible for the nth plus 1, nth plus 2, nth plus 3 data. Because r square always increases as we add terms in the model, some regression models builders prefer to use the adjusted r square, which I mentioned is basically by dividing by the degrees of freedom. So, adjusted r square would be given 1 minus. So, initially it was sum of the squares of the errors divided by sum of the squares of the total. Now, it will basically be n minus 1 by n minus p. P is basically k plus 1 depending of beta naught is there or not, multiplied by r 1 minus r square. In general, the adjusted r square statistics will not always increase as variables are adjusted to the model. In fact, if necessary terms are added, the value of r square adjusted would often decrease and basically give us an actual value of the prediction level of the model. So, now we will basically start off the test on individual regression coefficients and the group of coefficients. So, adding a variable to the regression model always causes the sum of the squares for the regression model to increase and the errors of the sum of the squares to decrease. So, obviously, we want as x's are increasing, r square would basically give us the maximum output, but obviously the question remains that to what level are we able to predict for the nth plus 1, nth plus 2 data point. That's point number one, whether the errors as per the assumptions have normally distributed with a zero mean and certain variance, whether the normality assumption holds and the covariances of the betas which you want to find out are really small or not, because if they are very large, obviously apart from unbiasedness, the consistency property would not hold. We must decide whether the increase in the regression sum of the squares is sufficient to warrant using the additional variable in the model. So, we will try to basically find out the hypothesis that rather than testing the significance of any of them collecting as a group, we will try to take them as an individual and try to predict to as maximum as possible. With this, I will end the 30th lecture and try to continue with these combinations of the hypothesis testing, such that we take individually the betas and try to predict whether H0 is true or HA is true, and basically pass judgments accordingly. Thank you very much and have a nice day.